Our next lesson is about VMC. VMC is a sea level calibrated airspeed at which if the critical engine were to be made suddenly inoperative, you'd be able to maintain directional control and thereafter straight flight with no more than 5 degrees of bank toward the operative engine. The manufacturer is in charge of determining the VMC speed for their airplane based off some parameters the FAA sets for them. The old regulation for what manufacturers had to comply with when determining a VMC speed was 23.149. The new regulation is 23.21.35 Charlie. What's included in the regulation that the manufacturers have to comply with is the acronym COMBATS. When determining the VMC speed, the manufacturer must comply with COMBATS to publish their VMC speed. The manufacturer must determine the VMC at when the critical engine failed and windmilling. Our airplane does not have a critical engine. We'll talk about this in a little bit of a later video. Next, they must determine the VMC speed with the operating engine at max power. The airplane must be at the most unfavorable weight. For this scenario, it'll be the lightest weight possible. And the bank angle cannot exceed 5 degrees of bank. In addition, it'll be tested with an aft center of gravity and a takeoff configuration with the flaps and the gear up. Finally, it's tested for a standard day. Now, this is what the manufacturer must comply with when making the VMC. The VMC speed for our aircraft is 65 knots, but that is a fluid airspeed and it will change. We're going to discuss now why VMC speed changes and how it. Our next topic is discussing how VMC changes and the factors that impact VMC. First, we have standard day. We're going to discuss two altitudes, a high density altitude and low density altitude. When discussing these factors, there's three main key parts to determine if VMC will increase or decrease. First is the factor, second is the performance, and third is the controllability of the airplane. The first is high density altitude. At high density altitude, performance is going to decrease. Performance decreases at high density altitude because we have a naturally aspirated engine. As we go up in altitude, there's less air for the combustion process. However, controllability is going to increase at high density altitudes. Why? Imagine that you're kicking a football in Denver compared to kicking a football in Jacksonville. In Denver, there's a lot less air friction on that football, therefore it can go farther. In Jacksonville, there's more air friction on that football, causing it to not go as far. Now let's tie this back to controllability. At high density altitudes, there's less air impacting the control surfaces, making them more effective, therefore increasing the controllability of that airplane. As controllability goes up, VMC is going to decrease. You're going to see this as a common pattern with all these different factors. As controllability goes up, VMC goes down. And as controllability goes down, VMC goes up. Our next topic is low density altitude. At low density altitude, performance is going to increase. We're a naturally aspirated airplane, and therefore, with more air, we're going to get better performance. Controllability is going to decrease. Why does controllability decrease? There's more air friction impacting control surfaces, making them less controllable. Finally, VMC is going to increase with low density altitude. Our next topic is takeoff thrust. Takeoff thrust is going to increase our performance. We have more thrust, we have more power, we have more performance. Controllability, however, is going to decrease. If I have my left engine and my right engine, and my left engine's at full power, it's going to yaw the airplane quite a bit more, therefore making the airplane less controllable. VMC is going to increase at takeoff thrust. Next, we have an aft center of gravity. Remember back to your commercial check ride. With an aft center of gravity, performance is better. Why is performance better? We have less drag on that aircraft with an aft center of gravity. Controllability, however, is going to decrease. With an aft center of gravity, we have a shorter lever arm. The shorter the lever arm, the less controllable the airplane is. Imagine I'm a baseball pitcher. When I pitch the baseball, I don't leave my hand here and then throw. I try to cock it back as far as I can and then throw. This increases controllability because we have that longer lever arm, so we have better control of the airplane. However, for the aft CG, we have a short lever arm, meaning we have less controllability of that airplane, increasing our VMC speed. The next topic is engine windmilling. A windmilling prop is inefficient. It's creating more drag on that airplane. Performance is going to decrease. In addition, controllability is also going to decrease because we have more drag on that airplane. Therefore, VMC increases with the engine windmilling. Our next factor impacting VMC speed is using 5 degrees of bank. In the event of an engine failure, we're going to turn 5 degrees toward the operative engine. Why do we do this? Because when we put that 5 degrees of bank in, we're aligning the longitudinal axis of the airplane with the relative wind. If I were to use only bank or only rudder, I'd be making that relative wind in the side direction, creating more drag. With 5 degrees of bank, performance increases because I straighten that longitudinal axis to the relative wind. Controllability increases, causing VMC to decrease. Next are flaps. 2 different topics here. Cowl flaps open and wing flaps up. When my cowl flaps are open, performance goes down because I introduce more form drag. More parasite drag, more form drag on that airplane. Controllability, however, is going to increase. Why does controllability increase? Because we now take advantage of the keel effect. The keel effect lowers that center of gravity, makes that airplane more stable when the cowl flaps are open. VMC is going to decrease with cowl flaps open. Next, wing flaps up. When my flaps are up, performance increases. However, controllability is going to decrease because we lose that keel effect the flaps were providing. VMC is going to increase. Retracted gear. When I bring the gear up, performance increases. Why? Because we no longer have the drag, the form drag that those gear were producing. However, controllability is also going to decrease in this situation because, again, the keel effect. We lose the keel effect, controllability decreases, VMC increases. Out of ground effect. When an airplane leaves ground effect, performance and controllability both decrease. Why? Because that airplane is having to generate more lift than it was in the ground effect, causing our performance and our controllability to decrease. VMC will increase. Max gross weight. When I have a heavy airplane, performance decreases. A heavier airplane is less efficient. Go look at your performance charts of any airplane, you'll see a heavier airplane is less efficient. Controllability of the situation, though, is going to increase. It's harder to move a heavier airplane. So it's going to yaw less, so we're going to feel the effects less with a heavier airplane, causing VMC to decrease. Now, the last 3 sections, as you can see in your book, is trim set for takeoff, full rudder or 150 pounds of force, and recovery within 20 degrees of the initial heading. Now, these are all standards that are set by the FAA. Trim must be set for takeoff. We can apply full rudder, 150 pounds of force to maintain directional control, and we're recovering within 20 degrees of the initial heading.